Hey everyone, welcome to PrepFusion. So today we'll be starting the lecture 14 of state space chapter, right? So in the previous lecture, what we learned about the controllability. What do we mean by controllability, and how do we find controllability of a system, and many different examples. Like we took many different examples. Okay. So in this lecture, basically we'll try two topics. One is Kalman's test for controllability and Gilbert's test for controllability, right? And before starting that, right, so in the previous lecture, right, I told you that we have to measure all the state variables, okay, for the system to be totally controllable. Okay, so let's just a bit of proof, right? Not like a total proof, just a bit of intuition. I want to give you, like, why do we need to measure all the state variables. Okay, so I will write the topic here is like the just before the main topic, subtopic, why do we need to measure all the state variables? Why do you need to measure all the state variables, right? Okay, so basically so why do we need it? So I will take an example of a diagonal matrix, okay, diagonal system matrix, and with the help of that I will explain it to you. But I will explain it according to that matrix, but for a different matrix, right, that rule won't follow. Okay, that rule won't follow. We have to use the Kalman's test. Just for understanding and bit of intuition, we'll use diagonal matrix. Okay, so here, right, let's say I have state equation. Okay, and what happens in a diagonal matrix? How are they how is the system matrix written? It is written in terms of eigenvalues, right, and other elements are zero. That is it is basically a diagonal matrix. So the diagonal elements will be my eigenvalues, okay, and my other non-diagonal elements will be basically zero, right, as it is a diagonal matrix. Okay, and this is my state variable, okay, state vector basically, and we have a input. Let's say that this input is something like this, okay, 0 0 1. Let's see what happens. So this is 0 0 1. Now I want to write this, like I will only write the state equations, so I will write the state equations in equation format, right, not in matrix format. So right, what will be my x1 dot of t? X1 dot of t will be simply equals to lambda 1 into x1. X2 dot of t equals to lambda 2 into x2, and x3 dot of t will be equals to lambda 3 into x3 plus u, right? Now what is the important thing here? The important thing here is basically, right, if I change my u for some reason, I take some feedback and I change my u, then only I can control the change in state of x3, right? From this u, with the help of this u, I can only control this x3 if I change this u. But the other change in state of variables, right, x1 and x2, my u is not present here, right? So even if I change my u, right, this state won't change. This state will change only according to its own state variable, that is x1 only. Okay, and this state will only change according to its own state variable and its eigenvalue basically. Okay, so yeah, but this one I can control. Okay, this one I can control with the help of input. Okay, the change in the x3 I can control with the help of input, but the change in x2 and change in x1 I can't control with the help of input. So that is the reason all of them need to be like measured, right? So we have to measure all of the state variables, then only we can basically control, right, control. That's why we say, like, we have to measure. Here we said, right, we have to measure where did it go basically? Okay, I don't think it is somewhere. Okay, where is it? Yeah, measuring all the state variables. So for that, right, I have to measure all the state variables, then only I can pass it to the this input, right? This input will be related to the change of state variable, then only I can do that, right? Because the relation there is given, like change in state variable is related with input, right? But there is no relation for the x1 dot and x2 dot. That's why we have it is not possible to measure the x1 and x2. Okay, so yeah, we will not be able to measure x1 and x2. In this case, there will be no relation between x1 and x2 and u. No relation x1, x2 and u. Okay, that's why it is not controllable, and we can't take feedback. We can't take feedback of these ones, right? Can't take state feedback basically. Okay, so as you can't measure, right? As you can measure. Okay, so this was one important point that I wanted to like convey to you. Okay, so now let's move to the main topic of this video basically. So the main topic is, first topic is Kalman's test for controllability. So this is basically a matrix basically. Okay, this is known as a controllability matrix or whatever. I don't remember the name actually, but you just call it like QC. Okay, so Kalman gave this test, right? So QC is defined like a matrix like this one. Okay, now you might ask, what is this colon and what is this? Once we solve the question, we'll understand. Just understand that this will be what the order of QC, right, will be n cross n. That is basically number of state variables or order of the system. And what will, like, how many terms will I have? I will have n terms, right? Let's say my system has order 2, so I will have this first 2 matrices. Okay, and if my system has order 3, then I will have 3 matrices. Okay, and you might say, why are this multiplied like this? This is the rule. I will like give you a brief proof of this one. Okay, not complete proof because that will make the video lengthy, but I will give you the intuition. Okay, and you might ask, like, this is AB and what is the semicolon? So each right, like this B is a column matrix, right? B is a column matrix itself. So this represent one of the columns of the matrix, and this AB, right, what is the order of the AB? I mean, what are the number of rows and number of columns of this matrix multiplication AB? So AB, right, AB has n cross n order, and B has what? N cross m, right? And most of the cases our m is 1 only, right? So if m is 1, then what is the order of this AB? AB order has like n cross 1. Okay, so yeah, this is my order of this is my order of AB, n cross 1. Okay, so what does this mean? This means that I have n rows and 1 column, right? So this is also a column vector basically. Okay, so this is also a column, this is also a column, and I have n, right? So yeah, basically it will be like a square matrix only, and each element right here, B will represent 1 column of that matrix, AB will represent 1 column of that matrix, and A square B will also represent 1 column of that matrix. Okay, so yeah, that was like the brief overview of this. Obviously we'll solve questions from there. You will understand what do I mean by this matrix, right? This may not come to you instantly, right? So first, right, what you have to do is we have to like give you a bit of proof, right? Bit of proof. So we know, what we know is that x of t, right? X of t is what? X of t is the Laplace inverse of the state transition matrix times the B times U of s, right? B times U of s. Now what is my state transition matrix like what is my x of t equals to? So if I take the Laplace transform here directly, right? So generally we don't do that. I told you to, I advised you to solve this one first, then take the Laplace inverse. That will be easier. But if I take the Laplace inverse right now, what will be my Laplace inverse of phi of s? What is it? It is the basically e raised to power at, right? E raised to power at, state transition matrix in time domain, right? Laplace inverse of that. So it is e raised to power at. Okay, now this B, right, B matrix is just a scalar. B matrix is not a function of s, so I can simply multiply B over here. I will not change the order. Okay, but U, right, U is a function of s, so I can't simply multiply this. What happens if there is multiplication in frequency domain? Okay, I told you the property. If there is a multiplication in frequency domain, then there will be convolution in time domain. If you don't know it, you have to just trust my word. Okay, this will be taught to you in signals and system subject, right? But if there is a multiplication in frequency domain, then there will be convolution in time domain. Okay, so convolution in time domain. Okay, convolution time domain, and I will convert this into u of t. This is input, right? So I can see my x of t is function of both input and this B matrix, right? Also this A matrix, sorry, this u is, it is function anyways, but the main thing is it is function of both A and B. So my x of t, basically my state variable, let me write here, state variable is a function of both A and B. Okay, so my state value is a function of both A and B. Okay, so there will be some matrix that will be related with A and B, and that will define the controllability and observability. I will tell, okay, controllability. Okay, so observability will depend on different matrices, that also will study. So my x of t, right, what I can write here is, so one thing is that like I will not show you the proof, okay, because that will just consume my time. This e raised to power at, right, this e raised to power at, I can break it down into series, right? Series of function. What is it? It is 1 plus e by 1 factorial, then a square by 2 factorial, like that. Okay, I can break it down. Now this will be convolved with this one. Then what I can do is, like, what do we make convolution? So if there is x of t convolution with y of t, or let's say h of t, then what does the convolution formula becomes? It becomes x of t times integration of 0 to t x of t times simply multiplication into h of t minus tau d tau, right? Okay, that is the convolution formula. Now if you do that, we'll get a matrix in the form like this one. So this, right, this will become, so my first term will be 1, right, then it will be a square by 2. Now 1 times b, right, 1 times b becomes b. Okay, then I have what does this become? Again, this becomes a by 1 factorial. Okay, if this becomes a by 1 factorial, then this becomes ab, right, ab. So that's why I get ab. Okay, then what is the like third term? It becomes a square by 2 factorial. So it becomes a square by 2 factorial. Now 2 factorial, I will take it to the other side. I will understand you. So let me write this first. This is a square b. Now this is basically, this will go until n raised to power minus 1 b. Okay, and this is basically, this will go on like this is some alpha function, which is a function of time, like the basic terms, right, that 2 factorial in the bottom and 3 factorial in the bottom, all this will come into here, right, all this will come into here. Okay, and this is some function that is defined. Okay, that is basically that integration part, right? Other constant things like a and b, all those things will come outside, right? Okay, so what will happen basically, this one, right, so what will this become? So this will 1 plus a by 1 factorial plus a square by 2 factorial, and it will go on. Now this is times b, and now what is happening now, right? So there is t also, right, there is t also, this is t square, all those things. So that's t, right? If I do the integration of this one with e raised like t minus tau, what I will do is I will only keep this one here, and this function of t and this integration part, I will keep this one here, because this will be constant. A times b is just a constant, not a function of time, not of anything, it is constant, right? So I'm keeping this outside, and all the other things I'm keeping here, right? Okay, for simplification. If you don't understand, then don't worry, okay, because this proof is not important at all. Just to give you a bit of intuition, why does this proof say whatever it says, right? Okay, just to give you a bit of intuition. So now, right, this will be something function of delta 1, okay, alpha 1, and this will go on till alpha n minus 1 t, as this will be a matrix of n cross n. Okay, this matrix order will be n cross n. Okay, and this is simply a matrix order of n cross 1. Okay, because finally, right, I will have n elements, right, n elements, because this will break down to like n elements. Okay, so a has order of n. Okay, that's why. So yeah, this is a function of time, and this is not a function of time. Okay, now, right, I want to revise you a bit, because if you don't do revision, then you will not understand why does the rule say like so. So you remember, right, we learned Kramer's rule. Okay, what does the Kramer's rule say? Kramer's rule say, right, that if you have 3 variables, and if we have one like those are related to like equation a1 x plus b1 y plus c1 z equals to d1, and like that a2 x plus b2, if I put it in matrix format. So for me to get a solution, right, what does the Cramer's rule say? Cramer's rule says that the value of x will be delta 1 upon delta. Now delta 1 is this one, delta is this one, and delta 2 upon delta, and like this, right? I will not explain it further. So for me to get a unique solution, right, like x, y and z has to give an unique solution. What is the first thing that we need to consider, right? So first thing for me, x to get a unique solution, that this delta, right, this delta can't be 0. This delta has to be some finite value. Okay, also this delta 1 also can't be 0. Okay, I mean if both of them are 0, then we get 0 by 0 format, right? So we have to check. So this delta, right, delta can't be 0. If delta is 0, then what is the solution? No solution, right? Because we don't have any solution, because one row is dependent of another one. We don't have enough equations, right? What does this delta 0 means? Means that this column is dependent on this one, or this row is dependent on this one. What does that mean? That means the two equations that we got were only one equation. Okay, were only one equation, because those are linearly dependent. Then overall, how many equations we have? We have two equations. But overall, how many unknowns we have? We have 3 unknowns. Can we ever reach a unique solution? No. From two equations and for 3 variables, we won't be able to find unique solution, right? We won't be able to find unique solution. That's why the delta can't be equal to 0. And here also, if you see, what is my xyz here? Xyz is this one, right? This is varying, right? So what is the main purpose of this one? So I forgot to tell you that this is a state variable, and what do I want? I want to find my state variable. I want to get to my desired state, future state, right, with the help of controllability. Like I want to give a control input, and I want to get a desired state, future state, right? This is my desired future state. Okay, and basically this is this is the time expression, which this is the d1 d2 matrix, right? And this is the controllability matrix, basically that A inverse, B inverse, C1. So I will explain it to you. So let me copy this one. Okay, let me copy this one. So if you see something identical, let me know. So this one is the equation relation, right? So okay, let me first write one more thing. So like for one more thing I should write here is, for unique solution, the delta should be not equals to 0, right? This is the important point to note here. So right, can I see some similarity? I took this matrix from here to here, right? So what should I do? I pre-multiplied the inverse. So here there will be an inverse, right? This will be inverse. Now we'll copy this previous matrix, okay, this one. So what do I see? Like these and these are similar, right? So like if delta is not equal to 0, then 1 over delta should also be not equal to 0, right? So the 1 over delta will also be not equal to 0, because this delta is finite. Obviously its reciprocal will also be finite, right? Okay, so that is the basic thing. So right, so here, right, this is the same thing, meaning that its determinant, it is an n cross n matrix, square matrix. That's why I cleared the order at first. Its determinant should be not equal to 0 for unique solution. Hence this delta, like this is known as the QC matrix, determinant should not equal to 0 for unique solution. Okay, so that's how the condition came, right? Obviously I didn't prove it, how this alpha naught alpha t and how I rearrange the equations, because that is of no use to you. But you should know that how this determinant, like condition came, right? This one is basically no use to you. Okay, so we'll now do it case by case, okay, and understand what happens if the determinant is not equal to 0, and what happens if the determinant is equal to 0. Okay, so this we understand. For unique solution, okay, this has to be not equal to 0, then I will get my x of t. Okay, then I will get a x of t, unique x of t that I wanted, right? Future state, right? Okay, so if this is 0, then what will happen? What will happen if this is 0? The states variable won't be controllable, right? Our system won't be controllable. State space representation isn't controllable. Okay, So that is the thing. If I am not able to get to my future state, a unique future state that I want to get through this control input, okay, then that means the system is not controllable. Okay, so yeah, let us do case by case. So we have first case, right? First case, what is the first case? First case is if my this determinant of this matrix is known as QC, right? So I should explain what is QC. QC is this one, right? Okay, I have already explained this one starting itself, I think. Yeah, QC is this one, so I hope you got it. So QC is this one only. So my determinant of QC should not be equals to 0, right? So QC is n cross n matrix. Okay, so what does that mean? The determinant is not equal to 0. Determinant not equal to 0 means it is a non-singular matrix. Okay, non-singular matrix. Okay, so what, like, if the determinant is not 0, then what will be rank? Rank will be full, right? Rank will be basically the order. Okay, so rank will of this matrix QC, if my determinant is not equal to 0, it will be n only. Okay, so now I'm going the reverse direction now. Okay, I will go in the reverse direction now. I told you the proof how this came. Now I will go in the reverse direction. If my rank of QC equals to n, then what does this imply? This implies that my system, right, or my state space representation is controllable. State space representation is controllable. So why do I say state space representation? Basically, right, if I represent my system in state space representation is not unique. I can represent my system in multiple state space representations, right? So for one representation, the system may seem controllable. For other representation, it may not. Why? Because I haven't, in that representation, I haven't chosen the minimal set, right? That's why it may seem it is not controllable, and here it may seem it is controllable. So it all depends on how, like, my state space is represented. Okay, that's why the matrix will be given, and from there you will check for the controllability. Okay, so what does this mean, that my state space, like, this is controllable? That means that the way I represented my state space, all the state variables, right, will be reachable to the from my input, right? Okay, that's how I will control it. We can control the poles, we can stabilize the system, okay, with the help of my input, right? Okay, so all those things we can do. So that is the main thing by controllable. Also, I told you previously also. So, like, I will give you a brief. Okay, so basically this means all the state variables are reachable from the input. Okay, all the state variables are reachable from the input if QC is not 0, if basically it is controllable, if my state representation is controllable. Okay, and or vice versa also we can say that all the state variables are reachable from the input, or all the, like, input is available to all the state variables. You can say it like that also. So with the help of this, we can control the poles, or we can make the system stabilize or control the state variables. Okay, I should say make the system stabilize. We can stabilize the system. Control the state variables. Okay, so yeah, this is basically what happens. Okay, so yeah, now let's go to the case 2, right? Let's go to the case 2. So what is the case 2? Case 2 is when my this determinant is 0, right? Case 2, when determinant is 0. Case 2, if QC is 0, then what will happen? If determinant is 0, then what is this matrix called? Remember, okay, if you have studied matrix in your like A12, you have obviously, you have forgotten. So what do you call this matrix? If the determinant is 0, it is a singular matrix, right? Singular matrix. This is the opposite of previous one. Okay, singular matrix. Now what will be my rank? Can I tell my rank? So will my rank be, obviously it will be not n. Okay, so what will be rank? Will my rank be n minus 1, or will it be 1, or will it be 0? Okay, so if you said this one, right, you're wrong. If you said this one also, you're wrong. If you said this one also, you're wrong. Okay, why? Because I won't be able to tell the rank without knowing the rows or columns, or without knowing the elements, right? But what is for sure I will be able to tell is that my rank will be less than n. Okay, rank will be less than n. So what does this define? Like, what does this mean? If QC is 0, if determinant of QC is 0, then rank of, oh sorry, not rank, then the state space representation won't be controllable. That is, my input won't be able to reach the state variables, or my state variables won't be able to reach the input, won't be controllable. Okay, so yeah, this is what we mean by controllable and non-controllable. Okay, so like this, what does this QC mean? So QC, right, QC is a function of A and B. It defines the relationship between input and state variable. So this is also, you can write that this matrix, right, I forgot the name, whatever, this QC is defines the relation between the input and the state variable, right? Because like it is defined with A and B and the change in state, so that is why. Okay, so defines the relations. These are just theoretical point. Okay, no need to stress much. Relationship between input and state variable, right? Okay, so that is basically what for the this Kalman's test. Okay, so now what we will do is basically do one question. Okay, one question, and from there we'll understand like how to apply this test, right? Okay, this is the question basically. So what is this question telling us? We have to check if the system can be made stable. Okay, we have to check if the system can be made stable. But how can we make a system stable? We can, what you can see is the eigenvalues are positive. Eigenvalues are positive. What does it mean? System is unstable, right? So we have to make it stable. How can we make it stable? By changing the eigenvalues, by making them on the left hand side of the j omega axis. How can we make it to the left hand side of the j omega axis? Basically, right, basically what you have to do is use the concept of controllability. If the system is controllable, then I will change my input to some reference input and take the feedback, and I will change this to left hand side. So this hasn't told us to the exactly poles where we want to keep the poles, but it has just said check if the system can be made stable. How can it be made stable? If the system is controllable, then only I can make the system stable, right? So what we'll do, so basically indirectly it is asking us to check for controllability, if the system is controllable or not. Check for controllability. So how do we check this one? So for checking this one, right, we'll use Kalman's test. So Kalman's test, right, Kalman's test. So now you will understand what does this mean. So QC, as this is a second order, right, second order system, because the n is 2, right? N is 2 cross 2, n is 2. So this is second order system. How many columns will be there? 2, right? Like how many, this will be B. I will start from B. This is the first column, and the second column will be A times B, and I will stop here, okay, as it is a second order system. If it would have been a third order system, where I would have gone to B, AB, then A square B, and I would have stopped there, okay. So yeah, that is basically my QC. So this is a 2 cross 2 matrix, right? This is a 2 cross 2 matrix, and basically, right, each of them are column matrices. Each of them are column matrices. Okay, each of them are column matrices. So what will be my A times B? So I got that I will have to, now what I will do, next step, like the procedure for doing Kalman's test, right? You know, this is my QC. Now you will find these elements, right? If there would have been a third element, first I would have find AB, then I would have again find A square B, then I would have written the QC matrix. That is my basic procedure, okay. So I will find AB. So what is my A? My A, right, is 1 0 0 3, okay. And what is my B? B is 0 1. B is 0 1, okay. So simple multiplication, 1, and this is 0 times 1 0, 0 times 0 0, 0 times 3 times 1 is 3, okay. This is 1, this big, oh sorry, this is like 1 times 0 actually, okay. So first element will be 0, sorry, this will be 0 only, okay. So this is 0 3. So now I got my EB element, and B is only single column, so that is easy only. So my QC, right, QC I can write like B is what? B is this one, right? 0 1. B is 0 1, and like my this AB is 0 3, right? 0 3. Now can you tell me the rank of this one? Can you tell me the rank? Is rank 2 or 1? If you find determinant, you see it is 0, right? And this, right, this column is totally 0. So this is basically rank will be 1, right? Okay, rank will be 1, because if I multiply 0 with this, I get this one, right? So these two columns are dependent with each other, okay. If all of the elements would have been 0, then rank would have been 0, okay. We have not got any space, right? Any space. It is just a point, nothing. This is 1 3, so at least I have a line. At least I have a basically not line. At least I have a point. If everything is 0, then we don't know. At least we have a point. 1 3 is a point, right? 1 3 is a point, okay. So yeah, my this rank is 1, okay. Or if you don't want to go to rank, the simple thing is just check the determinant, right? So my determinant, right, QC will be 0, right? QC will be 0. If you calculate the determinant, it is 0 times 3 minus 1 times 0. Simple only. You go with determinant. If you get confused, don't go with rank, okay. Don't go with rank. I am recommending you go with determinant, okay. It will be simpler and it will not cause you headache in your mind, okay. So that, what does this mean? The system is uncontrollable, okay. Uncontrollable. So what does this mean? We can't make the system stable. So what would be my answer? We can't make the system stable, okay. So this will be my answer, okay, as system isn't controllable, okay. So now we'll go to the next topic. The next topic is basically controllability for diagonal matrix, right? So the easiest way, like this was one of the way for checking like a controllability. Second way is, if we haven't given a diagonal matrix, right, then we can directly from seeing the matrix itself, I can say whether the system is, whether the representation is controllable or not controllable, okay. So this x dot of t I can write here is the like the equation I will again write, okay. But there is also another test that I will explain to you, okay. From the test also we will understand. So this is simply ax plus bu and y equals to cx, okay. D I'm just ignoring it, okay. Now what I will do, I will make the transformation, okay. So this is my normal thing. So for like if you want to check controllability through other method, right, that one is the first method from Kalman's test, okay. But if you want to check from other method, that is this method, so what you have to do is convert this matrix into diagonalize it, okay, into diagonal matrix, as we learned right in previous lecture how to diagonalize it. Basically we will have some p eigenvector matrix, okay, and then we will use a transformation. How we used to transform it? Basically, right, what we used to do was x equals to p times x bar, right? X equals to p times x bar. So basically, right, so if I do the transformation of this one, so I will put the value of x here, okay, and then I will use the transformation that will diagonalize my matrix, right? But the main point is you don't have to do it, okay? You don't do this. If in the question you have been given a diagonal matrix, then only apply this rule that I will tell you in the next few slides, okay, that you apply. But there are a few caveats, there are a few warnings that I will tell you after that also, so just be careful. So that Kalman's test is always safe option, always, it always gives correct answer. And if you are not understanding anything, and if you are very confused and very like freaked out or something, then use Kalman's test, because that's simple only. Just find AB, multiply, then find the determinant, just simple procedure. This gives the result faster, but there are few caveats also that I will explain, okay? So what is the main thing? So I will again do the transformation, right? This will become x bar of t equals to ap x bar plus bu, and this becomes x bar of t equals to p inverse a p x bar, and this becomes p inverse b u, and this y, right, y also becomes c px. So this anyways changes, c p x bar, so this changes anyway. So what does this represent? I hope you still remember the eigenvalues and eigenvectors chapter. This represent basically we are diagonalizing this matrix, diagonalization, okay. If there is some mistake in my spelling, so please forgive me, okay. So this is diagonalization, right? So this is the basic equation. So now this all we know, just to give you a brief like overview, right? Just to give you a brief overview. So how my matrix looks like? So my matrix, right, after diagonalization, my matrix elements will look like this, right? So let's say I have a third order system, okay. This one was like x1 dot x3 dot x3 dot, okay, and here I have, okay, I think I've already written it down, okay, I think I've already written it down, yeah, this is okay, sorry. So that we understand, right? So this is after diagonalization. What will happen? My eigenvalues will come over in this A matrix and other elements will be 0, basically diagonal matrix. Basically we already know this one, right? So we have done this in parallel decomposition also, we have done, okay. So all these things we know, right? So my form will be something like this. Just here I have two inputs instead of one, okay, fine. Just to take a bit of a different example. So now, right, what is this Gilbert's test? What does this Gilbert's test tell us? So Gilbert's test, right, so first I will write the state space equation, then you will listen. Gilbert's test basically tells us is that along the row of this one, right, along the row of this eigenvalues, even if like all the elements are 0, right, what do I mean? So let's say this lambda 1, right, along this lambda 1 row, if this b11 and b12 is 0, then this state variable won't be controllable, okay. This specific state variable won't be controllable, but we have to answer as a whole, right, answer as a whole of the state space representation. So what will answer? If along this row, this b complete row, first row is 0, okay, for the B matrix the complete first row is 0, then the state space representation will be not controllable, okay, it will not be controllable, okay. So that is basically by just looking at the matrix I can say. So let's say this lambda 2, right, along this row, the B matrix, the second row is 0, so all the elements of the second row are 0. Then what I can say, right, that basically this system won't be controllable. So all the elements of this, like, or not all, okay, at least one element of each row has to be non-zero for it to be controllable. So what should I mention here? At least one element of each row, at least one element of each row should be non-zero. Okay, at least one element of each row should be non-zero. That is the main point, like Gilbert what tells. Okay, but the caveat here is this is for non-repeated eigenvalues, but you might say then what happens for repeated? We'll see there are few exceptions, right, for non-repeated eigenvalues. Okay, so yeah, now you might say like how did came. I've already like explained a bit, like in the starting of this lecture also. I took a diagonal matrix and there I told you, right, that one element can't be zero. That is the same thing, right? Same thing, that even if one element is zero, right, I won't be able to control the variable, right, state variable. Just here I just started the lecture with this example, actually this one, right? I took this, okay, diagonal matrix I took, okay, on the same example, and what I told, if there is no relation between x1 and x2, I won't be able to take the state feedback, or I won't be able to control the state variable change of state with the help of input, right? Then I won't be able to reach my desired state, right, for this particular state variable, okay, for x1. So as a whole my system will be my state space representation won't be controllable. Okay, so from that example you understood, so I won't again do another example, okay, that is already repeated. So now, right, let's check for repeated folds. What happens for repeated folds? So okay, where am I here, right? This one I just did. Okay, so what happens for repeated folds? For repeated poles, right, basically I will take help of Kalman's test, and then I will explain it to you if it is controllable or not controllable. Okay, so using Gilbert's test, what we can say, so if let's say we have one state space representation of second order system x1 dot of t and x2 dot of t, which is simply equal to, let's say this is -2 0 0 -2, right, and this is my x1 x2 plus, simply let's say this is like this is any a and b, okay, and this is non-zero, so a and e is not equals to 0, and sorry, not b, a is not equal to 0 and b is not equals to 0. So according to Gilbert's test, right, Gilbert's test, what can I say, that this statement read at least one element of each row should be non-zero. Here at least one element of each row is non-zero, and this is a diagonal matrix, right, so these are non-zero. So according to Gilbert's test, it is saying that this is controllable. Okay, so then okay, I should write here, complete the statement also. I forgot to complete the statement. Then the system would be controllable, right? Okay, then the system would be controllable if like at least one of the element of each row of B, actually I should say here each row of B. Okay, I am missing few by B matrix. Okay, each row of B should be non-zero. Okay, then the system would be uncontrollable. Okay, this is the point. Okay, so here like the as I told, right, this is non-zero and this is also non-zero, so my system will be controllable. Okay, according to Gilbert's test. So here I can write according to Gilbert's test, is it really controllable? Then let's check. State space representation. I shouldn't write system here, actually I should write state space representation. this is a long thing. Okay, sorry for the delay. I should have written it earlier also. State controllable, right? Okay, that is what I will write here also. So I will just copy this one. State is already there, sorry. Copy this one. Is controllable, right? Okay, my state space representation is controllable. Okay, so now now let's do it for the Kalman's test. So what does the Kalman's test say here? Like, it always gives the correct answer. Okay, just because of calculation we may ignore it sometimes and use different methods like Gilbert's test. Okay, so what does the Kalman's test say? So this is a second order, right? So my QC, what will be it? It will be simply B and AB, right? Okay, and this is basically 2 plus 2. Okay, so what is my B? B here is simply AB, right? AB. Okay, and like I have to first find the like a small AB. I have to find the matrix multiplication of AB, right? So if I find that, basically, right, this is minus 2 times A and 0 times B. So this is minus 2A. This is 0 times A, this is minus 2 times B. So this is minus 2B. Okay, so my AB is this one and B is this one. So my QC, what does it become? QC is simply AB and minus 2A and minus 2B. So what we can see? We can see, if we even find the determinant, you will see that it is 0, or what you can see is these two columns are dependent, right? Columns are dependent. Okay, hence rank will be 1, or just go through determinant. My QC, right? QC will be 0. Okay, QC will be 0. Okay, so yeah, this is basically my thing basically. Okay, this is basically the main thing. So yeah, so now, right, so like QC is this one. Okay, so yeah, what do we see here? If determinant of QC is 0, what does this mean? This means my system is uncontrollable. So according to, so I will write here, I will just change this statement a bit. It's not system, state space representation. Basically, according to Kalman's test, it is saying my system is uncontrollable, right? Uncontrollable. So obviously, which one is correct? I told you the answer already. Kalman's test is correct. Okay, Gilbert's test, you have to check other condition also. So now we'll check Gilbert's test for repeated eigenvalues. So Gilbert's test for that was for non-repeated eigenvalues. Now for repeated eigenvalues, right? For repeated eigenvalues, what does this mean? This means there should not be more than, okay, like read the statements. I will explain one by one every term, right? There should not be more than one Jordan block for same eigenvalue. That means for repeated eigenvalues. So I should say here, like for repeated eigenvalues, just read the statements. I will explain each of them slowly. Okay, elements corresponding to last row of Jordan block should be non-zero. Okay, this is also another thing. Now what is unknown, like what term is unknown here? Jordan block, right? You are saying that I don't understand what is Jordan block. What does Jordan block mean? So I will explain it to you. What does Jordan block mean? Okay, but like what are these two except the Jordan block? There should not be more than one Jordan block. So in a matrix there should not be more than one Jordan block for repeated eigenvalues, and elements corresponding to the last row of Jordan block should be non-zero. Okay, so elements of B matrix, I should say elements of B matrix. Okay, so yeah, so let's first understand what does a Jordan block mean. So whenever there is repeated eigenvalues, right, we solved using parallel decomposition. What used to happen there, like above the repeated eigenvalue there used to be one right, one x, instead of 0 there used to be one. Okay, 1. Now what does Jordan block means? So Jordan block will continue throughout the repeated eigenvalue until there is 1 above. Okay, until there is 1 above. So we have a question. So what does the question tell? Find the number of Jordan blocks in each of these matrices. Okay, we have to find the, like, this is like a matrix, right? A matrix. So there should not be more than one Jordan block for repeated eigenvalues. So in the A matrix, I should say in the system matrix, in the system matrix or in the A matrix, right? In the A matrix, basically. Okay. So all these are defined for A matrix. Last row of Jordan block in A matrix, basically. Okay, this should be in A matrix, or like A matrix you can also say system matrix. Okay, so yeah, this is basically that thing. So let's solve both of us. Okay, you also don't know Jordan block, I also don't know Jordan block. Okay, so like the elements where this 1 is present, right, up until this 1 is present, that will be one of my Jordan block for repeated eigenvalues. So let's first like there are multiple matrices. Let's first take this example, right, this one. So I will say how many Jordan blocks I have. Okay, so first what I will check, I will check that how, like, do I have repeated eigenvalues? Yes, this is 5 and this is also 5. This has repeated eigenvalues, right? And this is 2 and 3. Okay, this is 2 and 3. So yes, I have repeated eigenvalues. So what I will do, so what does Jordan block means? So these are repeated eigenvalues and we have 1 above. So this is the last row for this one, because after this we don't have 5 anymore, right? We have 2. So that is a different eigenvalue. So if a different eigenvalue comes, the Jordan block ends there only. So this is one of my Jordan block. Okay, one Jordan block. And what is another Jordan block? So my another Jordan block is this one, right? Because these are non-repeated. Okay, and this is my third Jordan block. Okay, because these are non-repeated basically. Okay, so this is my second Jordan block and this is my third Jordan block basically. Okay, we have only 3 here. Okay, and this is the main thing, right? This is one of the Jordan block. Okay, like okay, let me mark it like this one. This is one of my Jordan block. This is my another Jordan block, only 2, and this is another Jordan block, only 3, right? So yeah, I hope you understand. So like I should okay, this one go like this one. Okay, this 3 will be we get confused. I should like, okay, I should bring it like this. I hope you understand. This is 3, right? Okay, I should write like this is the second Jordan block. Okay, and this is the third Jordan block. Okay, okay, so yeah, this is basically my third Jordan block. Okay, so yeah, now right now, like, what will be the answer for this one? Number of Jordan blocks is 3. Just hold on a second. Jordan blocks is 3. Okay, and now let's go to the second, right? Second option. What is my second option? second option is this one, right? So if second option is this one, so let me, okay, I took this one also. So this, right? So how many Jordan blocks do I have? So I see two repeated eigenvalues, but do I have a 1 over here? No, I don't have, right? I don't. So this Jordan block will only end here, right? Will only end here, as I don't have a 1 over here. And this also will be another Jordan block, even though they are repeated, but I don't have one above, right? So only one above will will be the will continue the Jordan block, basically, not end, continue. So I have one Jordan block, so this will continue, but after this is not repeated, so anyways this will be one Jordan block. This is 4, but as this 4 doesn't have one above, so this Jordan block, right, won't continue, it will end here only, and this will be my another Jordan block. So number of Jordan blocks here is 2. Equals to 2, right? Okay, I should not write is here. Equals to 2. Okay, so yeah, basically, right, so this is my number of Jordan blocks. Now let's go for the third example. If I go for the third example, so as I can see, these are repeated, right, and they have one above it, so this Jordan block will continue up until this point. Then obviously we have a different eigenvalue, so we'll stop, and this will be my another Jordan block. So this will be my first Jordan block and second Jordan block. So number of Jordan blocks, okay, I will copy this one only, I will not write again and again. Okay, 2. Okay, and then this is my fourth option, right? This is my fourth option. So again, right, what I can see here is this is continuing, I have one above, but this is repeated eigenvalue, but I don't have one above, so my Jordan block will stop here only. So I will stop my Jordan block here. Okay, stop my Jordan block here, and again, right, I will continue start from here, and I see this is also repeated and I have one above here, so this will be my another Jordan block. Okay, so I have another Jordan block. So how many blocks I have? Again, right, 2. I have 2 Jordan blocks. 2 Jordan blocks, right? So like I should write this like this one, like draw this I drawn it a bit wrong actually. So Jordan block, I should draw it like this one, then this is my another Jordan block basically. Okay, and this is also my another Jordan block, right, this one. Okay, so I have 3 Jordan blocks. Okay, so yeah, basically we see it like this. So we have 2 and 2. Okay, so now, right, I will go back to my okay, this is the fifth, this was the fifth. Okay, this we have another one also. Okay, so let's see, like this one also, how many Jordan blocks we have. So again, right, this is repeated and we have one above, so this is one of the Jordan blocks. Okay, and this is the another Jordan block, right? So we have 2 Jordan blocks again, so number of Jordan blocks is 2 again. Okay, so number of Jordan blocks is 2 again. So like, yeah, we understood what does a Jordan block mean, what does this all mean. Okay, but now, right, let's like understand the statement now. So what does this mean? There should not be more than one Jordan block for repeated eigenvalues. Okay, now, right, this is one, like here there is one Jordan block and these are like one Jordan. Now for repeated eigenvalues, there should not be more than one Jordan block. What are the repeated eigenvalue here? It is 5. And how many Jordan blocks does it have? It has only 1, right? So yeah, the first statement, it is satisfying. Okay, first statement, it is satisfying. Okay, Gilbert states for state space representation to be controllable. Okay, let me write this. Copy this from somewhere. State space representation, I've written it somewhere, right? Yeah, this one. Paste this here, paste this one here. Maybe I should have just written it. Okay, let me change the color of this one, cut this one. Okay, and paste this one here. Okay, let me first reduce the size here. Let me first bring it down a bit. Okay, then paste it here. Okay. Okay. Color this one. State space representation to be controllable, right? To be okay, to be controllable. So yeah, it becomes a bit hectic here actually, so let me like bring this a bit down more. Okay, let me also bring this a bit down. Okay, so yeah, this is basically what this means, Gilbert's test. So as we can see, this has only one Jordan block for the repeated eigenvalue. So first criteria is satisfying, second criteria I will come to. Okay, now this has two Jordan blocks for the same repeated eigenvalue, right? So this is not satisfying the first criteria, so this is gone, right? This is gone. The system is not controllable. Okay, from the E matrix itself I can say. Okay, I will not have to even look to the B matrix here, right? I have one Jordan block for 3, that is the repeated eigenvalue, and another for another eigenvalue. So number of Jordan blocks even though is 2, but for repeated eigenvalues the number of Jordan blocks is 1 only. So here I should also write Jordan blocks for repeated eigenvalue. Eigenvalue, it is basically 1, right? 1. Okay, here, but here it is changing, right? Here it is changing. Here it is 2. 4 is the repeated eigenvalue, and here we have 2 Jordan blocks, right? 2, right? And here, how many number of repeated eigenvalues I have? I have only 1, right? I have only 1. Okay, only 1. And here also, one thing I noticed, this is the repeated eigenvalue, and I have 2 repeated Jordan blocks, right, for the repeated eigenvalue. So again, this, by seeing just this, I can say it is not satisfying the first criteria, so definitely this state space representation would be controllable. Okay, so yeah, this will be 2 again. Okay, so this will be 2 again. So let me change the color of this one, okay, to distinguish this from the previous one. So yeah, this is basically what my repeated eigenvalue is. So yeah, that was the basic concept, right? That was the basic concept. And like why like now let's check for like this is what you understood. Now what is the second condition tells us? The second condition tells us the rows corresponding to the Jordan block, right, they should not be they should be non-zero, right? They should be non-zero. Okay, the elements corresponding to the matrix or last row of the Jordan block should be non-zero. So if you would have taken an example, we would have understood. Okay, that we will take an example, and from there we'll understand, right? So but first what we'll do is like we'll do one question, and from there we'll understand. So this is one question. Okay, now this is the simple question for simple diagonal matrix, right? Okay, so we have to check for controllability using Gilbert's test. Okay, and we have another question, I think here. Again we have to check for controllability using both Gilbert's and Kalman's test. Okay, like this is the example that I took. Okay, so basically, right, here we have a Jordan block basically. Okay, if you understand, this is not a simple diagonal matrix. So again we'll apply the Gilbert's test for the other two rules, right? That for repeated eigenvalues we'll apply that and check for controllability. So I'm giving you these two questions as homework. You do this. Okay, do like using this Gilbert's test, you check, and that like Gilbert's test is easy only, you check using Kalman's test also, both of them, and tell me like think like why is this controllable and why isn't this controllable. I have already explained it to you also, but you try to draw the state diagram, and from the state diagram you think that why is this controllable and why isn't that controllable. Okay, what is the difference between the both of them, right? What is the difference between the two of them basically. Okay, so let's see what we learned in this lecture. Okay, so basically, right, firstly we learned about the Kalman's test. Okay, before that I gave you an example of the state feedback, why we need to measure all the state variables, and I give you a brief overview of the proof of the Kalman's test like this one. Okay, and why my determinant should be non-zero basically, to get a unique solution, right? To get a unique solution for the state variable, I want to get to my desired future state. Okay, for that I use this. Okay, so yeah, I wrote a few points and we did a few examples. So what is a summary basically? Summary is like Gilbert's test. I will explain you with the help of questions in the next lecture. But the summary is, if you want, like if you are very confused, use Kalman's test. It will give you a straightforward answer. Okay, but if you want the answer quickly, you can use Gilbert's test if the eigenvalues are non-repeated. Okay, if the diagonal elements are non-repeated, okay, then you simply use Gilbert's test. And what does that test tell you? So that test tells you this, right? At least one element of each row of B matrix should be non-zero, then the state space representation would be controllable. Okay, this, like at least one of them should be non-zero, then my input can control the state variable, right? Then my input is related with the change in the state variable, then I'll be able to control my state variable. Okay, if we have a diagonal matrix which has non-repeated eigenvalues. So this is very, very important. Just like keep this in mind, right? Keep this in mind. For non-repeated eigenvalue, this rule follow, and for repeated eigenvalues we have other set of rules. I've already written it down. I will explain it in the next lecture with the help of questions. Okay, but you can skip that if you are not comfortable with it, right? So in the next lecture we'll do all those things. Okay, thank you for watching.